Well, some initial value problems that are nonlinear can be solved partly in that we can find the Taylor series solution to as many terms as we need with some kind of recursive process. Unfortunately, there's not necessarily a way to find the function that recursively defined Taylor series is a representative of. So still, though, we can get this Taylor series to as many terms as we desire. So first of all, just a refresher, what is a Taylor series? About a point C, or sometimes you would say with center C, is defined as the infinite series y equals y of c over 0 factorial, that's just to set up the pattern, plus y prime of c over 1 factorial times the quantity x minus c, plus y double prime c over 2 factorial times x minus c squared, etc., down all the way to nth derivative of y at c over n factorial times x minus c to the n, and then it keeps going. Or you can write it as a sum, the sum y going from 0 to infinity of the nth derivative of c, whatever n is in that particular path, over n factorial times x minus c to the n. Now, I don't know if you remember why that is a Taylor series of a function, but I'm hoping you might recall that this function and its Taylor series agree for all derivatives, every last one, and that means it actually is the function that this is the Taylor series of. So here's what we're going to solve using Taylor series. And so we're going to solve the initial value problem y double prime minus 2xy equals 0 with y of 2 equal to 1 and y prime of 2 equal to 0. So what we do is we assume the solution is of this form: y of 2, we're making 2 the center, over 0 factorial, plus y prime of 2 over 1 factorial times x minus 2 to the 1, plus y double prime of 2 over 2 factorial times x minus 2 squared, etc. y triple prime 2 over 3 factorial times x minus 2 cubed. So we already have y2, that was given, that was an initial condition, and we already have y prime of 2 as an initial condition. So we can get as many as we wish by differentiating our original equation. If you differentiated this, see this says y double prime equals 2xy, well then y triple prime is going to be first d second plus second d first, so 2x times y prime plus 2 times 1 times y. So this gives us a third derivative. Y to the fourth, we'll just take a derivative of this, right? So 2x times y double prime plus y prime times 2 plus a derivative of this, 2y prime. So we're going to wind up with 2x y double prime plus 4y prime. And since we know y of 2 equals 1, y prime of 2 equals 0, then we can fill in the details. Y double prime of 2 is 2 times 2 times 1, which is 4. See where we're getting that? 2 times 2 times 1, which, 2 times, yes, 2 times 2 times 1, which is 4. And we also have y triple prime, look, 2 times 0 plus 2 times 1, and so that's equal to 2. And for y to the fourth derivative, we're actually going to do the same thing. We've got it here, so 2 times y double prime, well, we already calculated that to be 2, plus 4 times y prime, and that's 4 times 0. So 2 times 2 times 4 plus 4 times 0, and that turns out to be 16. And we can get more terms than that if we want. We can just we take another derivative of this, and we get y5 primes, right? So anyway, the first 5 terms, counting the term that's 0, 1, recall that's from this, plus 0, that's from this, plus 4 over 2 factorial, recall that's our y double prime, here it is, over 2 factorial times x minus 2 squared, plus y triple prime. I'm trying to think where I found, oh, y triple prime is 2, right? See, it's right in here. Over 3 factorial times x minus 2 cubed, y fourth derivative, which is 16 over 4 factorial times x minus 2 to the fourth, and then simplifying each of those, you can see we get 1 plus 2 x minus 2 squared plus 1/3 times x minus 2 cubed plus 2/3 times x minus 2 to the fourth. And we've got our solution y out to 4 terms of the Taylor series that would be the solution of this equation. Now, do I know what this is the Taylor series of? And the answer is, of course, not. But at least I have a technique that will get me a Taylor series that could be much longer than this, because I can keep taking derivatives. I can make this go out to 100 terms if I'm patient enough, but I think I've just run out of the patience. Yeah, we'll do another one in the next video.